welcome everybody to this Tyndall talk, which is a joint presentation between Philip Murphy and Dennis Saladuka. And it's on a topic that it's exactly in the kind of thing that Tyndall research is aiming for the future. It ticks the box of very strong internal collaboration between the CIT CAPPA group and theory and modeling at Tyndall. And it also ticks the box of working with international collaboration. And saying tick the box actually is probably doing it a disservice, because it's a very interesting piece of work based on the fact that it is a joint collaboration between theory and CAPPA, and with input from one of the top US growth groups of Jim Harris's group in Stanford. And it's in an area of strong interest to myself, getting light out of germanium potentially as an optical source. So having now half introduced the talk, as background, I'll pass over to Tomasz to actually introduce the presentation.
Okay, thank you, On. So today I have a honor to make a short introduction. So we will present the story about the germanium integrated in the group 3-5 materials. And this particular activity started more than 10 years ago. At that time, I was the Maria Curie Fellow at Tyndall National Institute, and I was seconded to the Stanford University. Actually, Eon was the person who recommended me to the Professor Jim Harris, and they invited me, and I spent wonderful months at Stanford University. And after return to Tyndall, I brought several heterostructure samples from Stanford, because they have very unique apparatus which can combine group 3-5 and germanium together on the atomic level and the MBE growth. So after my return to Tyndall, we started with the Nicola Pavarelli, the PhD student in our group, to make the optical characterization of the structures. So we mainly did time resolved luminescence and temperature dependent luminescence. And after a couple of months, we have very clear data. But we couldn't understand our observables, because what we observed two different emission behaviors going from the different part of the samples. And after months of thinking about the explanation of this phenomenon, Nicola decided to send the desperate email to the DBOR, because he found the theoretical paper describing similar structures, and he asked for advice. He asked for access to the paper, because we didn't have this. And after a couple of minutes, Philip Murphy arrived to his desk with the answer that yes, that's myself who did these calculations. And since that time, we experienced the very scientific adventure. Couple of weeks of scientific adventures, and about this story in detail, there will be first presentation done by Philip, and then since that time, the real collaboration between the Tyndall theory group and CAPPA group started. So we, on this subject, we have several papers published, and it was number of conference presentations, and this reached to the point when the Professor Mantu, who died from Virginia Tech in US, contacted us, and he said that he is going to grow the very similar material for not maybe for optical purposes, but for the very fast and low threshold transistors. But he would be very happy to collaborate with us, because he found that we have quite good experience in the optical characterization and the theoretical characterization of the structure. So he proposed to apply for the under US island scheme. I need to share the Okay, can you see my screen? So that's the initial collaboration between Stanford, Tyndall, and CAPPA group, and then this led to application under U.S. Island Research and Development Partnership Program, and together with the Professor Mantle, who died, our groups from CAPPA and Tyndall and Myrta Gruning from Queen's University Belfast, we successfully apply for the US Island, and for the next 3-4 years we collaborate under this similar material, which initially was brought from Stanford, but for the different purposes. And that about this US Island project, that will be second talk done by Janice or Denis. And at the moment we are polishing the final version of the new application under the same scheme together with Virginia Tech. The same two groups from Cork, so it means CAPPA and Tyndall, and we have new partners from Ulster University, led by Davide Mariotti. So at this moment, I'm giving the floor to Philip. I hope I clarified what the scheme of collaboration looks like. Philip, the floor is yours. Please unmute.
Hi, I think you need to stop sharing so I can share the screen. Yeah. There we go. Okay, so welcome everyone. Where is my screen? Am I showing emails instead? Stop share. Let's see. Tyndall talk, share. There we go. So welcome everyone. Let's make it big. Takes a while. So yes, germanium grown on 3,5. Yeah, that was an interesting material at the time. It's quite an unusual combination of things. But so where are we going with this material? What is the point of this? So the idea of the project that was born from the second collaboration we had was to use this material for highly tuned band offsets in tunnel field effect transistors. So this is beyond CMOS territory. This means that this might be in your green fast computers of the future. We also want to get into optical coherence tomography. Now you might know from Thomas Piwonski's talk, this is a very versatile tool. You can use OCT or optical coherence tomography to diagnose glaucoma in the eye and other things as well. It's also being used more recently to diagnose coronary artery disease. And these applications usually require that the tissues that they look at are semi-transparent. We want to bring this beyond that to study tissues that are more opaque, like the brain and the lungs. This requires a change of wavelength in the material, and this source of germanium will be able to do this. So just a little introduction on what the quantum modeling team does and how we support experiments. What we usually do is start from an atomistic quantum mechanics based point of view. So we look at the interactions of the atoms, the electrons, the vibrations, the lights. So we start with the atomic positions, we calculate the energies, then we perturb this material, which gives us a sense of the dynamics of the electrons and the atoms and everything. This gives us a lot of information, a lot of quantitative information on the resistivity of the material, the thermoelectricity, the heat. You can get absorption and emission of light, and you can even go into quantum applications because you're considering the quantum mechanics. We also can look at the exchange of energy, the different exchanges of energies in this material. Say if you start with just the atoms and the electrons orbiting the atoms. we can apply an electric field or a pulse of light. In this case, I throw a pulse of light at the material. This will excite the electrons. The electrons in turn will transfer energy to the atoms, so excite the vibrations of the material. And this has an effect, visible effects on the material, on the properties of the material that can be seen by applying, say, if you apply a voltage bias, you'll see the difference. It gives insight into the electricity. And also if you apply, say, a pump probe, you will see the effects of what's going on. And that allows you to characterize the material really well. So in this talk, and this project has addressed these two combinations of materials between germanium and 3,5. So usually these two types of materials are separate and they have their own applications. Like silicon and germanium, they are group 4 materials, and they're used for, they're in the electronic industry, they're everywhere. They're used for diodes, transistors, sensors, but they have no light emission. And that's one of the things that people want to bring into the silicon fabrication, which is something that emits light. Gallium arsenide is not compatible with the silicon fab, but it's also widely used for lasers, for diodes, light-emitting diodes. And it has a very high electromobility that allows you to do also quantum applications. These two are not usually mixed together, but in this case, we're mixing them. At the time of when Nicola sent his email, I was finishing up a paper on and I have given certain talks on I was looking at this highly strained germanium. And at the time, that germanium was being sought for light applications in silicon, so to speak, in silicon technology. So this material, if you strain it quite a lot, you could get light. At the time, that didn't exist, but people were really looking for it. I was looking at it from another point of view. Like if you also strain this material, you can get a really high mobility. And I calculated that the mobility, and predicted at the time, that the mobility can be tens and hundreds of times larger than the mobility of germanium itself, which is quite big already. So say if you have 2% strain, you can get a 50 times increase in the mobility. So that's what I was doing. Just to understand how this happens, I'll just go a little bit into the physics with a simple analogy. I like to look at the electrons, the conducting electrons in germanium as roads on a mountain landscape, say like Switzerland. So near the lake, you have a flat road, easy to get to, no need to climb the mountain, and it's full of cars for that reason. If you climb up a bit, there's another road, which is, it's really fast road, they're really fast cars, but it's less populated because you have to go up and up on the mountain. Now in germanium, this band that is higher in energy is very much like the conduction band of gallium arsenide. So that's why it's quite fast. If you go up higher on the road, up higher the mountain on the peaks, you have another silicon-like band, which is slower. And it's not very populated, so it's not really important unless you're mixing silicon and germanium alloys. Now, if you apply a large amount of strain, say if there was an earthquake on this landscape and you have some plate tectonics, you can shift the position of the roads, the first two roads. So bring the germanium-like band higher in energy and the gallium arsenide-like band lower in energy and fill it with cars so you get a really fast material, with the added benefit that the cars can get off the road by emitting light. So you have light in germanium as well. So fast and light emitting. When Thomas and Nicola were studying this material, I didn't know they had this sample. What they had was, what Thomas brought from Stanford on the plane was a material that was grown on a substrate of indium gallium arsenide. Right at the same lattice constant of indium gallium arsenide, germanium was grown on top. So it was, germanium ended up being strained at 2%, just the right thing you need. And they were seeing what people wanted to see at the time which was light emission in this material. So that was quite exciting. So when Nicola sent that email and I joined him and Thomas for a cup of coffee, I was really excited because finally this material existed. Maybe they could measure, somebody could measure the mobility, but at the time it was also interesting because it was emitting light. But what was puzzling them at the time was that the same sample had two types of emission in different parts of the sample. So in one part of the sample, they had one energy of emission, and on another part of the sample, they had a different energy. What was going on here? So say on one part of the sample, it's not only the energy that was different, but also the behavior of the material, of the emission. What they saw was that the decay of the light was different. Sorry, for different frequencies, the decay was the same. So this is consistent with a type 1 photoluminescence, in which if you have here the conduction and band structure of this sample, for instance, where you have the quantum well in the middle, if you excite the electrons and holes, they get excited usually in the indium gallium arsenide, then they relax the energy and fall into the quantum well. And finally, they find each other easily in there, and they emit the light, which is the spectrum that we see up there. On the other side of the sample, the light emission was behaving differently. It had a different energy, but it also had different decay times for different frequencies. Now, this was not a puzzle for them at the time. Why this was happening? It was because this is consistent with type 2 behavior. The question was, why did it have type 1 and type 2 behavior in the same material, which was supposed to be uniform? So type 2, just to briefly explain what it is like, again, the electrons and holes are excited in the indium gallium arsenide, but only one of the carriers, or the electrons or the holes, falls into the well. Then this has to go around to find the hole, which is at the edge of the material, and then it finally recombines. That's why the dynamics are different. So when we were having that cup of coffee, the first thought was, well, when Tomek flew over with his samples, maybe the baggage handling was a bit rough. A big bag of golf clubs could have been thrown on the bag of samples, and it could have damaged the sample perhaps, or released the strain in some way in certain parts of the sample and not in others. However, I had been doing these calculations to know what the energy of the strain was doing to the band structure of the material, the electronic band structure, so what gives rise to the emission of light. And the calculations say that this wouldn't in no way be big enough to explain a type 1 to type 2 behavior. So we had to roll up our sleeves and calculate. So the calculations involved supercells, and I had to build the interface between germanium and the 3,5 material to calculate the band offset energies. So here I'm showing two extremes of what is possible. So on this side we have, in gray, it's the germanium, the indium or gallium, because it's an alloy, it's shown in blue, and the arsenide, the group 5 material, is in red. And as we can see here already, which is a hint of what could be happening, is that the interface, when you have a group 3 material bonded to a group 4 material, you can have you have a certain polarization there, which will affect the energy on one side and the other. So you have a plus to minus here. The other extreme, when you have an arsenide bonded to the germanium, you have the opposite case. You have a minus to a plus. Now, if you calculate those energies, in the first case, you get a type 1 behavior, and in the second case, you get a type 2 behavior. So this is explaining what's going on. Excuse me. Further to that, we wanted to see if the energies produced by this behavior explain the photoluminescence. Excuse me. So I calculated the energies. So going from a pure, so changing the interface between a pure 5 to germanium bonded material to an interface with germanium to valence 3 bonded material and everything in between, you can get the energies of the transition. So as we see here, the band offsets on the right show the transitions that are possible in a type 2 behavior. As we move to a type 1, the energies of the frequencies of the emission of light change quite a lot. Then we cross to type 1, and then they don't change that much. Then it's about uniform in type 1. This already hints at applications, because if you can control the stoichiometry at the interface, means that you can control the band offset to a very large degree, and not only the band offset, but also the light emission. This of course then has applications for tunnel field effect transistors, where you can tune the band offsets really well and really tailor those energies to produce your fast green computers of the future. But you also can control the emission of light. So how does this how do my calculations compare to experiment? So first things first was the type 1. So here we have the emission of light type 1, which is around 0.8, just above 0.8. And type 1 coincides very well with what is calculated. So this is great. Then type 2, which you have a transition around 1 eV, or 1,300 nanometers, coincides with this stoichiometry here. And it's great agreement between theory and experiment. But there's something new here. So the theory says that there should be another transition around 0.7 eV, which the experiment is not seeing. So what's going on here? What happens is that the detector of light used in the experiment is not sensitive in that range of frequencies. So Tomek and Nicola worked very hard to make it more sensitive in that area. They had to change a few things in the apparatus. And finally, they did manage to see that transition, which was there. And this is a great example of how if you have theory and experiment collaborating in the characterization of material at the same time, you can get much more out of characterization and have a much better results. So this ended up being PhysRev letters. It's a great paper. And attracted loads of attention. So summing up a bit of what you can do with this is, if you have interface termination control, if you can control whether it's arsenide rich or gallium or indium rich, you can really tailor your band offset to whatever you want to have pure light emission sources all the way to highly tuned tunnel field effect transistors. And this was great. So the story so far goes like this. It started with Tomek in Stanford, getting those Stanford samples, flying over to Cork, starting the photoluminescence, getting great results, but some puzzles, which over a cup of coffee, we started discussing at the quantum modeling team in Tyndall, and explained what happened. This led to a nice paper that attracted the attention of Virginia Tech. The guys at Virginia Tech were really interested, and that made them reach out to us to start a new collaboration on SFI Ireland. We reached out to Queen's to add some more modeling on the interfaces. And this led to a collaboration between Queen's, Virginia Tech, Tyndall and CAPPA, which led to a successful SFI US Ireland project on tunnel field effect transistors, in which Virginia Tech was doing the material growth, the characterization was done at CAPPA, and we at the quantum modeling team and Queen's also did the theory. So this really highlights one of the strengths of Tyndall, that if you can just go from one desk to another person nearby doing completely different things, but that could be related, you can get great collaborations out of this that can span out to form bigger consortiums outside of Tyndall even. So this finishes my part of the talk. If you have any questions, please wait until the end of Dennis's talk. If you have any questions regarding the physics or anything like that, please do reach out to me. So thanks very much. And Dennis, you're on. I'll stop share.
Hello, everyone. I'll continue this story on the germanium. All right, so as Philip mentioned, termination atom on InGaAs layer strongly affects on the emission from the following germanium layers. So the following samples were grown in Virginia in the group of montehodite with mostly gallium termination of InGaAs, which gives type 1 band alignment. Let's have another look in band structure of germanium. Unstrained germanium is indirect, as most of you know, with emission from L valley or slow track in the mountains from Phillips figure. And with increase of strain, gamma valley starts to move closer to L valley. And at some stage, it could happen that some cars from slow L valley could speed up to gamma valley and emit light. And with further increase of strain, potentially all cars will go to the fast motorway of gamma valley and give a lot of light from germanium. So I try to see this in the photoluminescence results, and here they are. So this is sample without strain, and you see that this emission corresponds to indirect L valley as expected, with peak depending on temperature going reasonably well to the calculations from K dot P, and it's a typical drop of intensity to almost zero at room temperature and so on. And if we increase a bit of strain here, well, not very big, but some amount of strain, you can see that in generally the situation doesn't change very much. It's also the case with temperature, redshifts, with increase of temperature. So it's very typical for semiconductors. However, if you increase strain a bit more, there is some interesting features appear. You can see that for the sample with 1.6% of strain, at some temperature about around 120 Kelvin, energy start to rise instead of going down, and it's pretty uncommon for semiconductors. And actually that's happening because some charge carriers start to appear in the gamma valley, and thus recombining directly as a direct bandgap semiconductor. And this also is proven by intensity dependence from this sample. So you can see that at room temperature, this sample start to emit actually sometimes even more efficient than at nitrogen temperatures. So it's pretty uncommon. So to let's put this on the energy diagram depending on strain, and you can see that 1.6% of strain should be actually enough to have only direct bandgap emission from the sample, but it's actually not happening, even though it's very close to crossover point. In fact, it is crossover point where you can see both direct and indirect behavior in the photoluminescence. But in fact, the actual strain sample is slightly less than expected. So to get more information about bands in germanium, we also used photoreflectance setup. It's a technique which tracks changes of reflectivity from the sample under laser perturbation. It's like the laser induces the electric field in the structure, which creates a Stark splitting, and bands are affected, and in the bands and affect the reflection. In practice, it's just simple reflection measurements from the material modulated by laser light. So it's pretty simple in acquisition, but need quite careful interpretation. In this slide, I show photoreflectance spectra at different level of strain, from unstrained to 1.6% of strain, and photoreflectance is actually sensitive to all bands in the sample, and for this reason you can see a lot of features here. We used a third derivative line shape model to fit the most prominent peaks, and here they are on the graph together with PL data, and you can see that all of them corresponds to gamma 2 heavy hole transition band, which is related to strong electron hole coupling of this band. Okay, let's now do the opposite. Instead of fitting experimental data, let's simulate photoreflectance for the sample. So this work was done together with Philip and in collaboration with the team of Mirta Gerning from Queen's College in Belfast. And you can see that simulated spectra is pretty close to the experiment. However, this simulation was done for the level of strain which is lower than expected from lattice mismatch. So in the end, both photoreflectance and photoluminescence show that it's slight reduction of strain in the sample. Some of you may notice that energies, experimental energies on the graph are higher than theoretical, and this can be explained by quantum confinement happening in the material. So now it looks quite better. In the very end of my talk, I'd like to show some recent results. We tried to do optical excitation from the sample with highest strain, and actually found Fabry-Perot oscillations from this sample. And it means we are very, very close to the lasing from this material. And I need to know that all of this is done at room temperature. So this is a closer look at them. They're a bit strange, by the way, because mode spacing is defining cavity around 91 micron in the sample, which is 9 millimeter wide. So it's not like defined cavity. But with this material right now, we are actually working on the laser structure for broad laser around 2 micron for optical coherence tomography application, what Philip mentioned at the very beginning of his talk. And we'll continue this job. Hopefully it will go well. Thank you all for your attention. Thank you.
Thank you very much, both Philip and Dennis, for a very nice overview of the work you've been carrying on over the last 10 years and more recently as well. Before opening for questions, just to remind everybody that there is another Tyndall talk this Thursday when Pádraig Morrissey will be presenting, giving overview of work related to the PICSAP, the photonic integration pilot line. So that will be at 11 on Thursday. And in the meantime, I'll now open this for questions to Philip and Dennis, and both are there to take questions.
Thank you, everyone.
Hello, Philip and Dennis. Z here.
Hello.
A couple of questions actually. So for Dennis, in your last sorry, just start with you. Yeah, so you lost a couple slides. You mentioned the FP mode. I guess, is this related to the interference between the germanium and the 3,5 interface?
Okay, so I need to explain this. This measurements was done with stripe excitation. So it's with a stripe excitation, and I was looking from the edge of the material. So this emission was not collecting from the top view; it's connecting from the edge. So it would be true though, but thickness of germanium is around 30-40 nanometers. And cavity length is still 90 microns, so it's way above that distance.
Okay, that's interesting.
Yeah.
Yeah. Another question is, so you grow germanium a strained layer on 3,5. So I just curious, how do you maintain or manage the crystal structure, crystal quality of the germanium, because it's under heavy strain. What's the dislocation or defect level? Did you measure this one or not?
All right, so this is rather material. I have the picture here from the TM just to show the quality of the germanium layer. But in fact, the key point here is to have a thin layer of germanium, so not to exceed the critical thickness. It's, yeah, I mean, this is complicated. This is complicated. It's a completely correct question. I mean, I'm not an expert here, but as far as I see, the key point is to make it clear and.
Can I make a comment?
Yes, please.
So the growth process is quite complicated. So there's only, I believe, 2 or 3 machines in the world who can combine the group 4 and 3,5 material. So first of all, you are growing the very high quality indium gallium arsenide material in the one chamber, and there's the other MBE reactor, which is connected with the ultra high vacuum tunnel, and you're transferring sample to the different reactor to grow the germanium thin layer. And then you need to go back with this thin layer to the 3,5 material to grow again the second barrier of the indium gallium arsenide. And yes, this is quite tricky, because first of all you need to take care about the interface. That's what Philip said. This is very important. Was the end of the top of indium gallium arsenide is group 3 or group 5, and then the most important thing is the critical thickness. What Janis said of the germanium. From the cross-sectional TEM microscopy, we can see for the majority of the samples, the germanium crystalline quality is excellent. But we also have number of samples when the critical thickness was extended too much, and there are cracks.
Yeah, thanks very much. Yeah, I guess if there's a dislocation or defects, then there will be some relaxation there. Then it will definitely affect your polarization, I would say, because this is actually quite similar to what we have in GaN system.
Exactly.
We have the polarization. We have spontaneous polarization and also piezoelectrical polarization. I guess it's quite similar here.
I think indium gallium arsenide is not the piezoelectric material, so we don't have such a strong effects like in nitride materials.
Yeah.
One question. Thanks. That's very nice talk. My question is, how do you assess the strain level in your material? Do you actually measure the strain germanium, or you just calculate it from the lattice mismatch between your substrate and the germanium?
Okay, so in this slide, I'm showing it's based on lattice mismatch, but which there are also measurements of XPS, which I don't show here because they were done in Virginia Tech, but they show pretty. They show no relaxation actually on the sample. So it means it's not like complete relaxation on the material, let's say. If your question is about that.
So you can characterize the sample, let's say, area, and assess the strain in different parts of the samples. Yeah, can you?
No.
No.
Can I, Nikolai Petkov here? Can I just give some comments from the structural characterization, I suppose? Really, it's not so easy to do strain mapping, I guess is what you're asking for.
Yeah. I was wondering if that's possible or not. Yeah.
Well, that's not so trivial. It's not easy. You need to go for things like holography, for example. Electron holography would supply information about the mapping of strain in samples like that. Okay, so that is quite a difficult technique. It's not done quite often. I would advise maybe you could reach out to groups in Toulouse in France. They have very much a very deep experience in electron holography for strain mapping. So that is a group that I may get you in contact to. I know some people there, but strain mapping is probably one of the things that you need here in order to really understand and link, because strain mapping would give you really direct evidence of the quality of the grown material, and would also give you some idea about the interface. And as far as I understood, the interface is quite important here. Specifically, I think you also would need something like atomic mapping, atomic scale mapping at the interface to prove the concept of what happens if you have different termination at that interface. So, I mean, the images that you have here in they're okay images, but you need to go at least a few orders of magnitude better in resolution in strain mapping and probably atomic resolution mapping of the interface. I mean, maybe that's obviously that you can't do probably that in Tyndall. I'm sure you can't do it in Tyndall, but you may cooperate with other people on that. Just a comment, of course.
Thanks.
Yep.
Hello, can I ask one question? One regarding theory and one regarding experiment. Regarding experiment, the question is, did you try to measure their lifetime? So I'm particularly interested in some traces of non-radiative recombination, in particular Auger recombination in your germanium-based, strain germanium-based emitting structures.
We have problems measuring lifetime for this sample because emission wavelength is above the sensitivity of our system. So our system is based on InGaAs photocathode, so it's sensitive until 1.4 micron. Well, in fact, 1.3, but 1.4 micron. And here we have emission around 2 micron, which is way beyond this point.
I see. So I can check. I can probably have collaborators in Stony Brook who can measure the lifetime in that range very well. Not very many people can do. I can ask them whether they would be interesting, because for me, what I'm interested in the non-radiative Auger recombination, that's what I can calculate. And thank you.